Okay, so now we shall be taking the last topic of this week 8, where we will be focusing on the unknown input observer. So first we shall recall the type of observer we had discussed previously, and then we shall highlight the significance of this unknown input observer. So for example, given the LTI system, let's say x dot is equal to ax plus bu, y is equal to cx. Okay, right? So for example, we have this one. Now in the observers, what we had seen so far, we did not have any additional term. Let's say we add a disturbance term with its distribution matrix E. Okay, so we had focused onto the issue of the observability, that we discussed the observability of the pair A comma C. Okay, so for this disturbance, let's say we have this plant with the input and output Y. So by taking these two measurements, we have designed an observer which gives us the estimate of the state, right? Now if we have this disturbance term here in the plant itself, then what would happen to the observer? So we can parameterize this one as, let's say, x dot is equal to Ex so this I can write as Ax plus, let's write this as B tilde, and this becomes my U tilde. Okay, my output term remains as it is. So now instead of giving only this U, I have to supply this U tilde if I want to design an observer for this system, right? So I would change here as U tilde, and Y would remain as it is, and this would give me the estimate of the state X, right? Now here you would notice that in this U tilde we have two input variables. One is the what we have been using so far is the control output U, and D, which is an external disturbance. So if I want to design an observer which can give me the estimate of the state X, then I also need to supply the information of the disturbance to my observer. Okay, but in many cases, as we had seen during the controller designing week, that many times we do not have the information of the disturbance. So if we do not have this information of disturbance, how we can still design an observer which can give us the estimate of the state? Okay, so this topic talks in this topic we shall see how we can solve this problem. So defining the problem statement concretely. So this part we have already seen, okay, without this additional disturbance term. So now we would be considering a system which we are calling as the disturbed continuous time LTI system, with ABC as the matrices and E as the distribution matrix of the disturbance. Okay, where X, Y, U are the state output and input vector, and D is the unknown input, or what we call the disturbance of which we do not have the information. But we have the information of the matrices A, B, C, E, which are known to us, having appropriate dimensions. So here the problem we want to solve is to have the estimate of the state of the system such that the disturbances have no effect on the state estimation either. Okay, so this formulation, what we have labeled as disturbed CLTI, is pretty much a generic formulation. So now one point which should keep attention, that here the distribution matrix E, we have assumed that it is a full column rank matrix. Okay, now if E is not a full column rank, then using this rank decomposition what we had discussed earlier, I can decompose this E matrix as the multiplication of two matrices E1 and E2, where E1 is now full column rank and E2 might not be. So in my new formulation I can write this as E1 with some variable v bar, where v bar becomes my e2 dt, and this v bar is now my unknown vector. Okay. Now second, which is pretty much important, that the term E of E times dt can also be used to describe an additive disturbance, as well as a number of other different kinds of modeling uncertainties. So one of the examples we would take this into the, when we will come on to the tutorial, that how you can model some uncertainties and some disturbances which are pretty much non-linear in this LTI system in terms of u and y. Third, so if you recall, in the output equation we have only considered that y is equal to cxt, but there might be a disturbance term in the output equation with its distribution matrix as ey. So to get rid of this issue, what we can do, that we can design a transformation matrix, let's say ty, in the sense that if I multiply or pre-multiply this whole equation by the matrix ty, such that my ty ey becomes equal to 0, and at the same time my tyc is not equal to 0. Okay, so I can write my, or instead of taking y as an output variable, I am now taking as y e, which is equal to tyc xt, and this would become my new C matrix, let's say C tilde. Okay. Another generalization. Now, instead of having the disturbance term into the output equation, we could also have the input term, right, in the output equation as plus dut, in addition to what we had seen earlier. So since this u is already measurable, we can take it on the left hand side and define new output vector as y bar, which becomes equal to yt minus dut, and finally it would again become equal to c times xt. Okay, so all these four formulations we can use the standard formulation what we had introduced. So now coming on to the definition of the unknown input observer, consider this disturbed CLTI. So we define an observer as an unknown input observer whenever its state estimation error E of t approaches 0 asymptotically, regardless of the presence of the unknown input disturbance in the system. Okay. So let's see. So the structure for a full order observer we described as is z dot is equal to fz plus tbu plus k times y of t, where x hat, the estimation of the state, is given by the summation of the zt plus h times yt. Okay, where z is the internal state of the observer, and we call it the full observer because the dimension of the state of the observer and the plant is basically remains the same. So here x hat is the estimated state vector, z is the state of the full order observer. Here we now need to design the matrices f, t, k and h, because the B matrix is already known to us. Okay, so these are the matrices to be designed for achieving the unknown input decoupling and other design requirements if we have any. So this is the block diagram description of this observer where you see that now the disturbance term, which we are calling as the unknown input, is only acting onto the system, but we are not taking any information of this input to our observer. We are only taking the information of the input, or let's say the control output, and the output of the plant. Okay. So let's see how we can compute the matrices F, T, K and H. So this was the LTI plant, and this is the observer we have proposed. Now in a similar way we can see whether the state estimation error actually becomes equal to 0. So in the earlier observer design, we have defined the estimation error as the difference between the actual state and the estimated state. So the next step is to take the derivative of this state as x dot minus x hat dot. Okay. Now here I can substitute this x dot to here, and after taking the derivative of this output equation of the observer, I will substitute it here. Okay. So here in the output equation you will see that the additional term I would get is dx hat is equal to z dot plus hy dot. Okay, and y is equal to cx, so I can replace it by cx dot. Then again I can substitute x dot here. Okay, so computing the error dynamics and simplifying, finally I would obtain these terms where we have this E dot is equal to some combination of this matrices times E of t, which is basically the state of the aerodynamics, this matrix times Z of t, which is the state of the observer. Here we have introduced k as equal to k1 plus k2 into this equation, and finally I can write this as some matrix times y of t, some matrix times u of t, and some matrix times d of t. Okay. Now this equation is pretty much important because what do we want? That the error dynamics should be equal to 0 under the presence of the external disturbance d. So if we make all these matrices, this one, this one, this one, and this one, if we make all these matrices somehow equal to 0, then we would be having only this E dot of t is equal to some matrix times E of t. Okay, meaning to say that the error dynamics now become completely, or let's say the error dynamics are now completely decoupled from the external disturbances. So what do we need to solve? We need to solve these four equations, which basically say the same thing, that hc minus I times E should be equal to 0. Now t should become equal to I minus hc, so that this term would go to 0. Here we are substituting the state matrix of the error dynamics as some F matrix, right? Meaning to say, so if, or let's say if my F becomes equal to this would also become equal to 0. Now see this part, this is my F. So if my K2 becomes equal to F into H, this part would also goes to 0. Okay. So the remaining part is E dot is equal to F times E, where if I ensure that my F is a Hurwitz matrix, then the error would become 0 asymptotically, meaning to say my state estimate becomes equal to the actual state. But the questions which further arises, that does a solution to equations 1 to 4 exist? Meaning to say whether we could be able, or we could solve these equations. As we had seen that these are the parameter matrices of the observer which we need to synthesize, F, T, K, and H. If there is a solution, then how we can compute the solution of these equations, and at the same time how to ensure that F is a Hurwitz matrix, because F is not the matrix which we are assigning or which we are defining. This basically comes from this part. Okay, so we do not know yet whether after designing my H and K, or how to design this H and K such that my F becomes a Herbert matrix, right? So we'll see the answer to these questions by equations, by taking equations one by one. So first of all, we'll take the first equation, which is HC minus I, where I is an identity matrix, by the way. HC minus I times E is equal to 0. Okay, so first we will see whether the solution of this equation exists and what would be the solution of this equation. So this is the one of the important results which says that equation 1 is solvable if and only if the rank of CE matrix becomes equal to the rank of E matrix, and a special solution of this equation is given by as H star is equal to E times this matrix. Okay, so now we'll see the proof of this theorem very quickly that how this equation becomes solvable if this rank condition is satisfied. So again, there are two parts of this proof. First is the necessity and another is the sufficiency. So we say that there is a solution H, and let's say H is a solution. Okay, implies that the rank condition is satisfied. So first we will see this part of the proof, the sufficiency part, that if the rank condition is satisfied implies that H is a solution. Okay, so when equation 1 has a solution H, I can write HCE is equal to E, because we have this HC minus I times E equal to 0. Okay, now this part I can also write as by taking the transpose both sides by combining the CE matrix. So CE transpose H transpose becomes equal to E transpose. Now pay attention to this equation. So I can write this equation as let's say CE, I call it A bar, and H transpose, let's call it X bar, and E transpose as Y bar. Okay, so we had seen these type of equations earlier. So let's write this in a common notation as Y bar is equal to A bar X bar. Okay, where Y bar is E transpose and X bar is H transpose, and this A bar is CE transpose. So if you recall the controllability week where we have introduced about the range spaces and the null spaces, so you would see that your Y bar should belong to the range space of this matrix A bar. Okay, now this Y bar is nothing but your E transpose, and this A bar is nothing but your CE transpose, meaning to say that E transpose should belong to the range space of the matrix CE transpose. And this leads to that the rank of this E transpose matrix, or the rank of Y bar, should be less than or equal to the rank of this A bar, right? Now if this inequality would also hold under, if I take the transpose both sides, that is to say the rank of E is less than equal to rank of CE. However, that the rank of this matrix CE should be less than equal to minimum of rank C and rank E. Okay, which would again be less than or equal to rank of E, meaning to say for example, if the rank of E is greater than rank of C, then the minimum of this one would be rank C, and then rank C is again less than rank of E. Now if rank of E is less than rank of C, and taking the minimum of this rank C and rank E would yield rank E, meaning to say that it becomes equal to rank E. So the rank of CE would never be greater than rank of E. It would always be either less than or equal to rank of E. Now see both these conditions. The first condition says rank of E is less than equal to rank of CE, and the second condition says that the rank of CE should be less than equal to rank E. And this becomes possible if and only if the rank of E is actually equal to rank of C, right? So this finishes the necessity part. In the sufficiency, when rank of CE equal rank of E, and we know that E is already a full column rank, meaning to say that CE would also be a full column rank matrix. Now if CE is a full column rank matrix, then I can take a left inverse of this matrix as, and which can be written as CE. We have used another denotation as plus. So C raised to the power plus becomes equal to CE transpose C inverse times CE transpose. This is basically the pseudo inverse of this CE matrix. So finally I would have H is equal to E pseudo inverse of CE is a solution to equation 1. Okay. So this finishes the complete proof of the theorem 1. So now we have the solution and we have the conditions under which this equation 1 can be solved. Now if once you have computed this H, you can directly compute this matrix T, because C is already known to us and I minus HC would give us the T matrix. Okay, so this is quite trivial. Now the third equation is F is equal to A minus HCA minus K1C. So now we need to see that whatever the H we have computed from the first equation, if we plug that H into this equation, can we show that my F matrix would be a stable matrix for some K1, let's say. So let's see. So the solution of equation 1 is given by this one, H is equal to E CE plus, where CE plus was defined as this. Now if we substitute this H into this third equation, that is to say A minus HCA minus K1C would become this one, where I have taken A as a post multiplying factor from the first two parts of this equation, that is In minus E C plus is H, C and A minus K1C. Now I substitute this whole part as A1, and so finally this F becomes A1 minus K1C. Okay, so now this equation you would see, which is pretty much familiar to you. We will summarize all the results later on, I mean into this slide. So given this plant which is having an additional disturbance term, we have designed this UIO ensuring that the solution of these equations exist where the key matrix is the H matrix. Depending on the H matrix, the further three matrices could be computed. Okay, the Hurwitzness of this F matrix is a separate part which we will see now. So this is the main result for the unknown input observer, that the necessary and sufficient conditions for UIO to be an unknown input observer for this system, that the rank condition is satisfied, of which the importance we had seen already, and the pair C comma A1 is detectable, where A1 is basically A minus HCA. Okay. So the significance of this first condition is that if this rank condition is satisfied, we can compute H. Okay, so this equation is solved if this first condition is satisfied. Second, we can compute the T matrix. Now if C or A1 comma C pair is detectable, where this one is A1, if A1 comma C pair is detectable, meaning to say F would definitely be a Hurwitz matrix. Okay, now so this equation matrix we can also compute whatever F we have obtained from here and H from the first equation, multiplying these two matrices would give me K2. So basically we have computed all these four equations, and the necessary and sufficient conditions for solving these equations basically is this one. Okay, so these four equations, which are the key equations for designing the UIO, here you would notice that we have not used K1 and K2 for any purpose. So basically K1 is a free parameter which basically ensure the Hurwitzness of this F matrix. So this matrix K1 possibly won't be unique. Now the interesting part of this UIO is that this UIO actually becomes a full order Leonberger observer if we substitute T is equal to I, H is equal to 0 and E is equal to, or under the absence of any disturbances. Okay, so this Leonberger observer we had seen earlier, we can see very quickly. So this is the observer. We have Z dot is equal to Fz and X hat is equal to Z plus Hy, right? So this is what we have as observer. So now if we substitute T is equal to Y, so this will go away as an identity matrix. H is 0, so this part would become equal to 0. So the remaining part is X hat would become equal to Z. So substituting Z by X hat here in the first equation, we would have X hat dot is equal to Fx hat plus Bu plus Ky. So this is the same observer we had designed in the starting of this week, where if you recall, instead of this K matrix we have used an L matrix. Okay, where we have also ensured the Hurwitzness of the matrix F. So we had discussed two methods. One is the eigenvalue assignment method, and as the Lyapunov method for designing this F matrix, F and L matrices. So as the necessary and sufficient condition, we need the F matrix to be a Hurwitz matrix. Now if this pair A1 comma C becomes an observable pair, then we can substitute any K1 matrix, meaning, or we can place the eigenvalues anywhere onto the left hand side by designing this K1 matrix. So we have more design freedom. Now if this pair is not observable, then of course by using the concepts we had introduced earlier on decomposition procedure, we can check the stability of the unobservable part, okay, which is here A22 matrix. So if the eigenvalues of this A22 matrix are stable, then with the detectability or with the observability of the pair A11 and C star, we can say that at least A1 and C is a detectable pair, so that we can carry forward with the designing of this K1 matrix. So if we see the entire procedure, so the first check condition is the rank condition, whether the rank of E is equal to the rank of C. If this condition does not hold, then the UIO does not exist, because this is a necessary and sufficient condition, and we will go to stop. Now if this rank condition is satisfied, we can compute this H matrix, and further we can compute the two matrices T and A1. If this pair A1 comma C is observable, we can directly compute this K1 using the pole placement technique, or either of the method we had discussed earlier. And finally we compute this F and K matrix, and then we can stop the algorithm. Now this step 4 is basically the decomposition procedure if the pair A1 comma C is detectable, so that we can compute this transformation matrix P, and using that transformation matrix I can obtain the observable part of this unobservable system. So checking the detectability, we can see if the A22 is unstable, then again the UIO does not exist and we can stop the algorithm. So depending on how many states are observable, we can assign the desired eigenvalues, and the rest would stay as it is. So again we can compute this F and K matrices, which would finally yield us the unknown input observer. Okay.